All right, welcome everyone. Today, we're going to start talking about our next major topic, and that's infinite series. So in this lesson, we're going to define series, we're going to define partial sums, and then we're going to see how we define the convergence of a series using partial sums. So there's going to be a lot of terminology here, a lot of new terminology. So by the end of this lesson, you're going to be able to write out the first few terms of the sequence of partial sums for a given series. All right, so first of all, what is a series? And, sometimes we call it an infinite series, usually just series for short. And it really starts off with an infinite sequence. So it starts off with this infinite sequence a sub n, where n goes from 1 to infinity. Just a list of terms. And what we're trying to do with a series is essentially we're trying to add up all the terms of our original sequence. So it's a1 plus a2 plus a3 plus a4 and so on. Just keep adding all the terms. Just keeps going and going and going. We're trying to add up all the terms. So the dots here really emphasize the fact that this addition, we want it to continue forever. All right, so we can write it out sort of in this long form here where we just write out the first few terms. Or we can use a more compact notation, which we call sigma notation. And this is where we use this capital sigma here, which really is a fancy addition sign. It means the sum. So we're looking at the summation of a sub n from n equals 1 to infinity. It's a sigma, it's a sum, just tells us we're dealing with a series here. Or sometimes when we just want to be a little bit more general, we just write sigma an for our series. So there's a few different representations for how we describe this. So essentially what we're doing with a series is we're trying to add up all the terms of an infinite sequence in a specific order. So when we try to add up an infinite amount of something, we have to be careful. And that's really what we're going to see over the next lesson, over the next bunch of lessons, is this process of adding up an infinite amount of terms can get tricky, can produce surprising results, and in general is, not necessarily an easy thing to define. So it can't always be done. So we're going to see series where the sum does not exist, where we really can't add up all the terms together. So if the sum does not exist, we say the series is divergent. But if the sum does exist, if we kind of get lucky and we can actually add up all those terms, well, then the series is convergent. And so when we talk about an infinite sequence here, or an infinite series, we really have to be careful how we kind of add the terms together. So it's going to take some thought on how do we actually add up an infinite number of terms. And just as a little example, more of a warning, just to see something, it looks like you should be able to do it, but you really can't. So let's consider the series. Let's take our alternating sequence, the one that bounces back and forth between -1 and +1. Let's see what happens when we try to add those terms together. So let's start with +1, then we'll subtract 1, then we'll add 1, subtract 1, keep going like this. So that's an infinite series. We're taking a sequence and we're just attempting to add up all the terms of that sequence. Now, what we're used to is let's write this out again. We're going to write it out 2 more times, but we're going to just see what seems plausible, but actually produces very different results. So let's write this out a couple different ways. And this example is going to show that infinite series kind of behaved a little bit differently than what we normally would expect with just regular addition. All right, so here's our original series. But in this first one, let's kind of add these two terms together. Our first two terms, plus 1, minus 1. We get 0. Then let's add up these two terms, plus 1, minus 1. We get 0. Then do it again, plus 1, minus 1. What do we get? We get 0. And so if we pair things up like this, we get 0, 0, 0. So essentially, we just have a whole bunch of zeros here that we're adding together. And we would expect, does this equal 0? Well, maybe someone else comes along and says, I want to group these a little bit differently. So I'm going to leave this plus 1 by itself, but now I'm going to group these two terms together. Add them together. I get 0. Then I'm going to group these two terms together. I get 0. And I can keep doing that over and over again. I could take this minus 1. There's going to be a plus 1 next. I could add those together, get 0, and kind of keep pairing them up that way. And in the end, I'm just going to have all these zeros, but I still have that plus 1 at the beginning. So it looks like if I were trying to add up all these terms, if I were to think of it like this, I would end up with positive 1. So there's something wrong here, because if this series, if the sum did exist, we shouldn't be able to add it up two different ways here and get two different results. So there's something fundamentally wrong with what we're doing here. So this is just a little example for something that feels perfectly, that we actually can do when we talk about adding up a finite number of terms. But as soon as we start trying to add up an infinite number of terms, how we group things and all the kind of usual rules that we use might not work out like how we expect. And that's what we're seeing with this series here. So in this case, this series we'll see is divergent. The sum does not actually exist. So this is just a little example for kind of what can go wrong when we talk about an infinite series. All right. So we need to talk about, well, how are we actually going to do it then? So we know adding up an infinite amount of terms is going to be tricky. So how we're going to actually do it, and that last example shows it doesn't really behave like our usual addition operation. There's something fundamentally different here. Sometimes we can add up infinitely many terms, but sometimes we can't. And so the strategy we're going to use, and we're going to see this next time in more detail, but our general strategy here is going to involve limits. So what we're going to do, how we actually are going to define the sum of a series, is we're going to take and we're going to add up a finite number of the terms of our series, of our sequence here. And then we're going to do the limit as n goes to infinity. So we've seen this idea before, where we first do something in the finite case, and then we let n go to infinity. So we've seen it before with improper integrals. We would take a improper integral where we were trying to integrate up to infinity, and what would we do? Well, we'd shrink it down to the finite case, and then we'd extend the interval out to infinity by doing a limit. And we're using that same idea here. Instead of adding up an infinite amount of terms, what we're going to do is we're going to add up a finite number of terms. That we actually can do. We know how to add up a finite number of terms. That's our regular addition. But then we're going to do the limit as n goes to infinity. So as we add more and more terms here. So step 1 is going to be add a finite number of terms. Step 2, we're going to compute the limit as n, the number of terms we're adding together, approaches infinity. And this right here, we're going to call a partial sum. So step 1 is we're going to figure out our partial sums, and then step 2, we're going to do the limit of our partial sums. All right, so let's look at our definition. What is a partial sum? All right, so we're going to start with our sequence an. And what the partial sum is we just take the first few terms of that sequence and we add them all together. So given a series sigma an, we're going to let our partial sum s sub n, this is going to denote the nth partial sum, and this is where we take the first n terms of our sequence and we add them together. So we add the first n terms of sequence an. And we add them all together. So we get s sub n. Another way to write this is sigma ai, where I goes from 1 to n. So I here we're using as our index. So it's a1 plus a2 plus a3 and so on. And then we stop when we get to an. So we actually stop here. All right, so let's try a few examples where we just calculate the first few partial sums for a given series. And how do we do this? So let's kind of look at, well, what actually is this, what's going to be a new sequence. We're going to call it the sequence of partial sums. So we're going to start with our original sequence. This is our original list. These are all the terms that we're trying to add together. And we're going to form a brand new sequence. This is going to be called our sequence of partial sums. And this is S1, S2, S3, and so on. So what is S1? This is just the first term of our original sequence, kind of just there by itself. S2, what is S2? Well, we take the first two terms of our original sequence and we add them together. S3, what's S3? Well, we take the first three terms, add them together. What's S4? We take the first four terms. So A1 plus A2 plus A3 plus A4. And we could keep doing this. So we could keep doing this as much as we want. S5, take the first five terms, add them together. All right, so there's going to be some different terminology here. So let's just kind of write out all the different things we're talking about so far. So there's our series, which is really A1 plus A2 plus A3 plus A4 and so on. So we're trying to add all the terms together in our original sequence. Then there's our actual original sequence. This is just the list. So it's A1, comma A2, comma A3, and so on. Yeah, do A4 as well. And then we're forming a new sequence, which we call the sequence of partial sums. And so what is this? Well, this is S1, S2, S3, and so on. No, let me put S4 in there too. And it keeps going. So when we talk about series and partial sums, there's kind of three different sort of related gadgets, topics that we're kind of discussing. There's our infinite series, which is what we get when we try to add all the terms together. There's our original sequence. This is just the list of all those terms. The series is when we actually try to add them all together. And then how we're actually going to calculate the sum of this series is by actually looking at the sequence of partial sums. And this is a brand new sequence. S1, S2, S3, S4, and we can find each of those by just adding progressively more and more of the terms from our original sequence. So there's these kind of three things floating around here when we talk about partial sums and series here. All right, so let's try a couple examples. Example 1. We're given this series. So 1/3 plus 1 over 9 plus 1 over 27 plus 1 over 81 and so on, where the nth general term is 1 over 3 to the n, or we keep adding. This is a series. This is an infinite series. And what we want to do in this example is we want to write out the first 4 terms of the sequence of partial sums for this series. All right, so let's do it. Let's start with S1. What is S1? Well, it's just the first piece here. It's 1/3. And let's actually write out the formula here. A1, which is 1/3. All right, what's S2? Well, we take the first 2 terms. So 1/3 plus 1/9. We add them together. Okay, not too bad. What's S3? Well, we take the first 3 terms, add them together. So we get 1/3 plus 1/9, but now we're going to throw in the third term, which is 1 over 27. So plus 1 over 27. All right, what about S4? Well, we take the first 4 terms and add them together. So A1 plus A2 plus A3. Now we're going to throw in an A4. So we have the first term, the second term, the third term, the fourth term. We're adding all those together. So 1/3 plus 1/9 plus 1/27 plus 1 over 81. And if we wanted to, we have all these written out. If we wanted to, we could kind of add these fractions together, consolidate them into one nice little fraction. So the first one is 1/3. What do we get if we add these two together? We get 4 over 9. What do we get if we get a common denominator and add these 3 together? We get 13 over 27. And then for the last one here, if we add these 4 fractions, get a common denominator, we end up with 40 over 81. All right, so here are the first 4 terms in our sequence of partial sums. So let's kind of summarize what's going on here. We have our original series. This is where we're trying to add everything together. What was our original sequence? Well, this is where we just list out all the terms that we're trying to add up in our series. So the first one there is 1/3, the second is 1/9, 1/27. So we're just listing these out. And it keeps going for forever. It's an infinite sequence here. So that's our original sequence. So the series is when we take all those terms in our original sequence and we try adding them all together. What we're doing here with these partial sums is we're producing a brand new sequence, and we call this the sequence of partial sums. So we're getting a brand new sequence. And what's the first term? Well, the first term is 1/3. What's the second term? It's 4 over 9. Third term, 13 over 27. Fourth term, 40 over 81. And it keeps going. We could keep going here. So we have these 3 things we're kind of talking about. We have our original series, which is where we're trying to add everything together. We have our original sequence, which is just those terms listed out kind of individually. And then we have our sequence of partial sums, which we get by just adding progressively more and more of the terms from our original sequence. All right, let's try another example like this. So in example 2, we're going to write out the first 5 terms for our sequence of partial sums. Here we're given the series sigma n equals 1 to infinity of 1 over n. So this is another way to represent an infinite series. Let's actually write out, though, this as kind of an infinite sum. So when n is 1, what do we get? We get 1 over 1, we get 1. When n is 2, we get 1/2, so it's plus 1/2. Then when n is 3, we get 1/3, so we get plus 1/3. And then n is 4, we get 1/4. N is 5, we get 1/5, and we're adding all these together. We keep going. The nth general term is 1 over n, and then we keep going from there. So that's our series, kind of written out 2 different ways. All right, so what's our original sequence then? Well, it's just the terms listed here, but we just list them out instead of trying to add them all together. So our original sequence is this sequence 1 over n, where n goes from 1 equals to n equal 1 to infinity. And so we could just list this out. So the first term is 1, the second term is 1/2, the third term is 1/3, 1/4, 1/5, and so on. And it keeps going. The nth general term is 1 over n. It just keeps going. So just like for a series, remember we saw sequences, we could either kind of write it in this more condensed notation, or we could just write out the first few terms. And what we're going to do is we're going to produce a brand new sequence, our sequence of partial sums. And this is going to be when we add progressively more and more of the terms in our original sequence. So we're going to calculate this. So let's start. What's S1? Well, S1 is where we just take the first term of our sequence. So it's 1. S2. What's S2? And let's actually write out the... Yeah, we did that. Yeah, why not? S1. What's S1? Well, it's just the first term of our original sequence, A1. So in our case here, it's 1. What's S2? Well, we take the first 2 terms, add them together. So A1 plus A2. What do we have here in our original sequence? 1 plus 1/2. So we're going to add those together. S3. What's S3? Well, we take the first 3 terms. A1 plus A2 plus A3. We add up the first 3 terms. So what do we get? 1 plus 1/2 plus 1/3. All right, what about S4? Well, S4, we just add up the first 4 terms. So A1 plus A2 plus A3 plus A4. We've added up the first 4 terms of our original sequence. So what are they? 1, 1/2, 1/3, 1/4. We add those all together. So 1 plus 1/2 plus 1/3 plus 1/4. And notice when you're doing this, we're basically taking our previous result and then just adding the next term. So we take our previous partial sum, 1 plus 1/2 plus 1/3. There it is again. And then we're just taking this additional term and adding it in, 1/4. And then finally, we want the first 5 terms. So S1, S2, S3, S4, S5. So this is where we just add up the first 5 terms of our original sequence. And what do we get? Well, we just take that previous result. So we add up the first 4 terms. And then we just throw our 5th term into the mix as well, and we add that in. And there we go. We've calculated all of these out. And that's perfectly fine. We could just leave them like that. But usually we want to try to simplify this down. And what do we get? So the first term, that's already nice. 1 plus 1/2, how could we simplify that? Well, I'll just get a common denominator. We get 3 halves. Over here, 1 plus 1/2 plus 1/3, get a common denominator. We end up with 11 over 6. And then for these 4 terms here, we add those together. We get 25 over 12. And then finally, if we add those 5 terms there, get a common denominator, we end up with 137 over 60. And so what we've done is we've found the first 5 terms, simplified, of our sequence of partial sums. So the first term is 1. Here it is right here. Then it's 3 halves. Then it's 11 over 6. Then it's 25 over 12. And then it's 137 over 60. That's our 5th term. And then this just keeps going. So we have kind of 3, when we talk about a series, there's the series itself where we're trying to add up all these terms together. There's our original sequence where we just have all those terms listed out. And then there's this sequence of partial sums. And this is when we progressively add more and more of the terms of our sequence together. And this keeps going on as well. So we use those little dots to indicate that this keeps going on. This is an infinite sequence here. All right. So next time, what we're going to talk about is the convergence of a series. And essentially what we're going to see is we're going to see how we can use, how we can use those partial sums to help us actually calculate the sum of a convergent series. So we're going to look at this definition next time. But going back to our example 2 here, we're going to see how this sequence of partial sums, how we can actually use it to answer whether this original series, whether we can actually add all these together or we can't. So we'll see that next time. All right, so enjoy the rest of your day, and we'll see you all then. Bye-bye.